Swayam Prabha. Digital India. Educated India.
We will continue from where we left off in the last class, okay? And we were looking at this term divergence of rho v v, okay? And how to evaluate it. Like I said, I mean, divergence of rho v v, remember, occurs in your Navier-Stokes equations, okay? And the momentum equation, conservation equation is a vector, momentum is a vector. So, you have to have the conservation equation for momentum written in all the three directions x, y and z, okay. And what we want to do is, we want to see how this term manifests itself in the x, y and z directions. That is the whole idea, okay. This comes in the Navier-Stokes equation. This is a momentum balance and has therefore three components. So, now we are evaluating this particular thing, okay, and I wanted to mention before I do anything, this VV term, this is called a dyadic product, okay. I mean, you are used to inner dot product, cross product. This is the dyadic product. There is no dot, no cross. I am just writing them side by side, okay. And how is this written? So, V is written as VI EI, VJ EJ. VI's are the components in the ith direction, okay. EI's are the thing, and I keep them different for generality. And therefore, divergence of rho VV is, the divergence operator is Ek d by dxk dotted, that is the dot product, okay, and rho is the scalar. So, rho Vi Ei Vj Ej. I may have used some other index last time, I am not sure, okay. I should have been more careful, but anyway, I will be consistent today. So, now when it comes to the dot product, and you have two unit vectors here, Ei and Ej, what you have to do is take the dot product of this term on the left, where there is only one unit vector Ek, with the one adjacent to the dot, which happens to be Ei, okay. So, Ek dot Ei will be non-zero only if k equal to I, okay. So, I am going to put k equal to I here, and so this becomes d by dxi of rho Vi Vj Ej, okay. All I have done is taken the dot product, Ek dotted Ei will be equal to 1 if k equal to I. So, I am putting k equal to I here, and whenever this becomes I, Ei dot Ei is 1, when they are not equal, it is 0, they does not contribute. So, now I want you to recognize that here I have a total of 9 terms, okay, because I am summing over I and I am summing over j, because j is repeated, I is also repeated, so I have 9 terms, okay. So, rather than write all the 9 terms, my interest is in writing the momentum balance in each direction. Okay. So, in the x direction, momentum balance, what is going to be the unit vector in the x direction? It is going to be E1. I am going to put, instead of j here, j will be 1. Okay. J equals 1, since E1 is the x direction. Okay. So, I am just putting j equal to 1 here. So, therefore, V also will be V1, and the right hand side now becomes d by dxi of rho Vi V1. I'm not writing E because it's already in x direction. Okay, you know that it's in the x direction. So, this is the unit vector in the x direction, which I am not writing because I will be writing for x, y and z automatically. Okay. If you want, you can put E1, it does not matter. Okay, E1 signifies E1 for x direction. Okay, now this is now going to be a summation of 3 terms. So, basically I told you totally 9 terms. In each x, y and z, you will have 3 terms each. Okay. So, what is this going to be? This is going to be d by dx1 of rho v1 v1 plus d by dx2 of rho v2 v1 plus d by dx3 of rho v3 v1. Okay. And you can use the product rule of differentiation. So, we can keep our life simple and right now say rho is not going to change with space. So, I can pull rho is constant, okay, incompressible liquid, okay, just for simplicity you can say if incompressible, then rho comes out, okay, I get rho times I need to have then derivative of x1 with respect to v1. So, what is that? So, I have v1 times dv1 by dx1 plus again v1 times dv1 by dx1. Okay. What have I done? I have just used the product rule for the differentiation. Use the same product rule for differentiation here. v1 dv2 by dx2 plus v2 dv1 by dx2. Again product rule of differentiation, okay, plus again product rule of differentiation plus dv3 by dx3 times v1 plus v3 times dv1 by dx3. Okay. I have just expanded the term. So, this is basically going to be the term which is corresponding to the divergence of rho v. What I want to do is rearrange some terms so that all these terms which are v, I guess this term dx1, these 3 terms I am going to combine together, okay. So, v1 times dv1 by dx1 plus dv2 by dx2 plus dv3 by dx3, okay, plus V1 dV1 by dx1 plus V2 dV1 by dx2 plus V3 dV1 by dx3. That is what I have. All I have done is done some rearrangement, okay, and the reason for doing that is I want you to recognize that this is, what is this? This is nothing but divergence of V, okay, and if you have an incompressible liquid, divergence of V is 0 from the continuity equation. So, this gets simplified, okay. This is equal to 0 from continuity. And so, basically divergence of rho V1 V1, one way to write it is to write it as V1 dV1 by dx1 plus V2 dV1 by dx2 plus V3 dV1 by dx3. Remember, I mean, what you are used to is V1 is U, V2 is V and V3 is W. For the, possibly you are used to that kind of a notation, okay, for the velocity components. So, and x1, x2, x3 are x, y, z, okay. So, you might see books, you know, using that kind of an expression, that kind of a notation. So, this is, all I am saying is, this is same as u du by dx plus v du by dy plus w du by dz, okay, because V3 is the velocity component in the z direction, that is w. The x3, the third spatial dimension is z. So, I mean, just a different notation I am using, okay. I have done it for the x component, you have to similarly do for the y component and the z component, the same thing. Put instead of j equal to 1, put j equal to 2, j equal to 3, you will get it, okay. Now, this particular thing that we have written here, this expression here can also be written as V dot gradient of V. So, I want to calculate V dot gradient of V, okay. So, this is, what is V dot gradient of V? How do you calculate this quantity? V again I write as Vi Ei, okay, and the dot remains as dot. This gradient is Ek d by dxk, okay, that is my gradient operator, and as acting on V, which is I forgot a j, let me put j, man, Vk Ek, okay. So, this is basically what it is. Now, so what is V dot del V? I have written the expression for V, put the dot here, this is the gradient operator and that is my V again. How do you calculate the dot product? Again, take the two unit vectors that are adjacent to the dot, I and j, and so I and j have to be equal, okay. I and j have to be equal, so I am going to put Vi d by dxi, that takes care of that, okay, and I have Vk Ek. So, this derivative is operating on Vk Ek, and again, because I am talking about rectangular Cartesian coordinates, the direction of the unit vectors do not change, it does not matter what position I am in space, okay. So, the Ek does not change, so So, that is not going to contribute. Ek is always a constant, E1, E2, E3 are constant. So, I mean they do not vary with space, that is what I mean, not constant, they are unit vectors, okay. The only thing which remains is this, again this is double summation, summed over I, summed over k, 9 components. I am only interested in the x component, let us say, okay. For the x component, put k equals 1. What do I have? Vi dvi by dxi E1, which is nothing but, now I am summing over I, which is V1 dv k equal to 1 dv1 by dx1 plus V2 dv1 by dx2 plus V3 dv1 by dx3. Okay. This term here is what I have here. V1 dv1 by dx1, V2 d1 by x2, this thing the same as this. So, this is nothing but V dot del V. Again you might see in different books people are using del dot rho VV, people are using V dot del V if it is incompressible. So, that mathematically is exactly the same, okay. However, when you are trying to solve some problem numerically, okay, let us say you have a complex flow. Now, it may matter whether you use this form or whether you use this form, okay. So, there are subtle points which you have to, so theoretically they are equivalent, because when you are doing an analytical derivation like I am doing on the blackboard, okay, things are perfect, but when you are doing it numerically, running a code on a computer to solve some flow problem, there are likely to be sources of numerical error, okay. And people believe this formulation is better for the inertial term. So, let me try to say this maybe a bit more clearly. The LHS can be d by dt of rho u plus divergence of rho u, okay, or it can be rho times du by dt plus u dot gradient of u, okay, of the Navier-Stokes equation. These are analytically exactly equal as long as your liquid is incompressible, because divergence of u is 0 from the continuity equation. So, you might say, look, left hand side can, for an incompressible liquid both of them are exactly the same, but when it comes to writing a code, there are people who believe this formulation is better than this formulation, okay. So, I mean there are subtle things which arise which you maybe have to be aware of. So, you may say they are equivalent theoretically, yes, but mathematically this may be more conservative, so this may be superior. Is this clear? So, both of these are equal. This is the left hand side of the Navier-Stokes equation, okay, and I just showed you that divergence of rho u, one term is continuity, that goes off, okay, and you have to sit down and see what I am saying is right, okay. So, now what I want to do is just talk about one more thing, and then we will talk about that surface integral. UV, this is a dyadic product and is written as UI EI Vj Ej, or can be written as UI Vj EI Ej, okay. This is got a total of 9 terms, correct, because you are summing over I and j. So, that totally 9 terms. So, you already saw this is one way to write it. Some people like to write it in the form of a matrix, because matrix, a vector has 3 components, you like to write it in the form of an array, right. A 3 by 3 matrix will have 9 elements. So, you can also visualize this as a matrix if you are more comfortable that way, okay. So, this can be written as a matrix U1 V1, okay, U1 V2, U1 V3, U2 V1, U2 V2, U3 V3, oh, 3. So, this dyadic product is, so again has 9 elements, it has 9 elements, right, and I am saying these are the, so this is like your 1 element, 1 2 element, this is the matrix representation of UV. Okay. So, I think what I want you to understand is that U and V are vectors, they have 3 components, okay. When you talk about a dyadic product, it has 9 elements, okay, and one way is to write it this way, and maybe it is easy for you to do dot products. Sometimes it is easy for you to use this matrix representation, because I might talk about, you know, something being symmetric. So, then you can understand in the matrix form what is the meaning of symmetry, okay. We will talk about the symmetry later. So, I want you to understand both these representations of this dyadic product, and this thing is also called a tensor, okay. This is also called a tensor. Okay. So, now, so this is just to tell you a little bit about how we need to handle vectors and dot products and stuff like that. I am now going to go to the Reynolds transport theorem, okay, and talk about that one term which we have not analyzed so far, which is the surface integral term, okay, because I spoke about the body forces, I spoke about everything else, I did not talk about the surface integral term. So, we will talk about the surface integral. So, RTT d by dt of rho v plus divergence of rho vv dv equals rho g dv plus over the control surface T dA. Okay, that is the Reynolds transport theorem. What we did was, just to recall, these are the things associated with the control volume. This is like your, what you are used to possibly, this is the accumulation term, and that is the net in the control volume, what is the net efflux of momentum across the control surface, that is what this is, and this we are saying is equal to the forces which are there, which is your generation term, okay. So, that is the body force, that is this thing. Now, this is true for any control volume, okay. I can choose my control volume to be arbitrary, I did not tell you this is my control volume. So, what I am going to do is, I am going to allow my control volume to shrink in size, make it very, very small. Okay, I am going to make it infinitesimally small. See, what are we trying to do? We want to understand what are the equations which help me derive the variation of velocity, pressure from point to point. So, I want to know how things are varying locally at every point. Okay. So, I am not interested in average big changes. So, I want to know how does the velocity change as a function of x. I want to know how does velocity change as a function of time. Okay. So, every x I want to know the position. So, I need to make my control volume as small as possible. That is what we did, if you remember, when I did the divergence, the equation of continuity, I said it is valid for any arbitrary control volume, and then I derived the equation of continuity from Reynolds transport theorem. Okay. From Reynolds transport theorem, we wrote it, we converted the surface integral to volume integral, and then wrote the equation of continuity. So, same thing we want to do here. So, I want to do it for as small a control volume as possible. So, consider the control volume tending to 0. Okay. So, what I want to do is volume, so there is a characteristic scale, length scale of the system. Okay. So, let L be the length scale of the system. So, the control volume will scale as L cube, because that is how volumes are, right. So, control volume is going to be of order L cube, whereas control surface is going to be of order L squared, because area scales as L squared. We are talking about infinitesimal quantities, epsilon, okay, very, very small, 10 power minus 5, 10 power minus 20, whatever epsilon you want to choose. So, if the control volume that you are talking about is going to scale as L cube, then this guy, all these quantities, okay, small control volume, this will be whatever this quantity is multiplied by a volume which is of order L cube. This is also a volume integral of order L cube. This is of order L squared. Okay. Clearly, in the limit of L tending to 0, L cube is going to go to 0 faster, okay, because it is an infinitesimally small quantity. So, this guy, all these things are going to be 0. What that means is the integral over the control surface has to go to 0, okay, for any arbitrary control volume. Okay. So, my point is that these volume integrals, all these volume integrals are of order L cube, the surface integral is of order L squared. Remember, L is of order epsilon, or what do I mean by 10 power minus 10, let us say, okay. So, the first term will be 10 power minus 30, second term will be also the volume integral, right, 10 power minus 30. The first term on the right hand side is also 10 power minus 30, and then I have the T dot dA term, which is of the order 10 power minus 20. Okay. In the limit of L tending to 0, making smaller and smaller and smaller, I am saying that these guys will go to 0, but this is not going to go to 0. So, I say integral of the control surface T dot dA equals 0 as, or T dot T dA as L goes to 0. Okay. So, T is, what is T? T is the surface force per unit area. Okay. T is now, it is a force. Okay, it is not, and well, this was a force balance which we wrote. This is a vector. So, this is also force per unit area. T is force per unit area, and this is, I am going to call this stress vector. Okay, I mean force per unit area is stress. Okay, and I am going to call it a explicitly says a vector, because tomorrow you will see that there is something called stress tensor. Okay, so this is force per unit area, and this is my stress tensor. So there is no dot or anything here. This is dA is the area element. So take a small area element. What is the force acting? The force will act in all three directions. That is T. Okay, that is the force per unit area. Now, what I want to do, so what we have shown is that if you have a particular point very close at a particular point, take a small control volume around that point. If you take an integral of the forces which are acting on the surface, that is going to give you 0. Okay, on the whole surface, the forces acting on that control volume are going to be 0. Okay, that is what we have shown in the limit of L going to 0, in the limit of an infinitesimally small control volume. What are the implications of this? Okay, this particular thing, integral over the control surface of T dA equal to 0, is called the principle of stress equilibrium. Okay, and this implies that the stress acting at a point along a surface at a point, okay, at a point along a surface is decided by the surface. That is, if we have two surfaces passing through a point or close to it, then the stress vector will be different. Okay. So, I think I am trying to tell you that if you take a particular point and there is a control surface, you take a point on the surface, what is the stress there? It depends upon the orientation of the surface. If it is independent of the orientation of the surface, then you won't be able to satisfy this thing. So, point is, if you take two different surfaces, okay, since you want to satisfy that condition, integral of the surface is 0, okay, you will the surfaces are different, the orientations are different, the outward normal is different. You need to have different values for the stress vector. Okay, otherwise you won't be able to satisfy that condition. So, if I have that, this is the point here. Okay, this is S1. This is one surface I have drawn S1. The normal to this here, this is S2. The normal to this is N2. What I am trying to tell you is that there is a point of intersection of these two surfaces. Okay, I have drawn a one dimensional surface for ease of visualization. So that, and if you talk about the stress there, it is not unique, it is determined by the surface on which it is acting. So the stress acting on this surface is going to be different from the stress acting on that surface. Stress acting on S1 is different from the stress acting on S2. Okay, so that's the point I am trying to make. Okay, stress acting on S1 and S2 are different, and therefore when you try to talk about stress, specifying the stress, you have to specify the surface, and which is normally done by specifying the outward normal. Okay, you specify, when you talk about specifying the stress, you talk about the surface by specifying the outward normal direction and the direction of the stress itself. Okay, hence a stress is specified by specifying the direction of the outward normal to the surface and the stress. Okay, so those are two things you have to specify, and basically that is the reason one looks at the shear stress as a tensor, because I need to specify two things, the direction of the outward normal and the direction of the stress. So in the matrix notation you saw some matrix element, right? There are two indices for a matrix, 1 and 2, A12, A13. So the first one will tell you the direction of the outward normal, second one tells you the direction of the stress. Okay, so I am just trying to connect different pieces, so when you read it peacefully, you will be able to hopefully make the connections and understand things better. So the point is, so it may appear to you that you need some infinite representation, right? Because from a particular point you can draw infinite amount of surfaces, and you need infinity of representations for describing the flow. But that's not the it's not necessary to do that, and that's what I'm going to show. So how does one get an idea about the T, okay, using the principle of stress equilibrium? That's what we are trying to show now. Okay, so maybe is one thing for me to look at. Take a same point here, take one surface like this and take another surface like this. Okay, this is O, A, B and O, C, D, and this is the point of intersection. If this is a two-dimensional case, okay, and what will be the surface integral I am looking at? I am looking at integral of T dA over, one is OAB. OAB is one surface, must be equal to 0, must be equal to integral over OCD T dA. Right? All I have done is I have taken two surfaces, OAB, OCD, it's a closed surface. Now from the principle of stress equilibrium, this has to be equal to 0, this has to be equal to 0, as long as the surfaces are very small, the volume is very small. So now my point is, I can write OAB as what? The range of T, okay, OA plus average of T over AB of. Let me explain what I have done, okay. I am trying to make things more clear, but now I am thinking I am going to confuse you people, but it is okay, equal to 0. So, what does this T represent? This represents the average, okay. This symbol represents average. So, when I am calculating the surface integral, I am saying the surface integral, the average of T about AB multiplied by this plus average of T over this segment plus average of T over this segment must be 0, okay. Because it is an infinitely small element, I can write this, make this approximation like you do numerically when you want to calculate the integral, okay. So, similarly, if I write for this, so what is the average of the stress? It will depend upon these two quantities. I can write for another surface, I can write the same expression, a similar expression. I am trying to tell you that I am getting two different values, okay, depending upon the orientation of the surface. That is the point I am trying to make, okay. So, if I do this integral over OCD, right, so if I take this integral over OCD, then what do I have? Integral over OC, oh wait, average of T over OC multiplied by OC plus average of T over CD multiplied by CD plus average of T over OD multiplied by OD must be equal to 0. Is this clear? See that the entire control surface I have divided into 3 parts: OA, AB, BO, OC, CD, DO. Okay, I am looking at 2 situations passing close to the point or exactly at that point, and when I take the average, if you were to calculate the average using this, you will get a different value for this value for T of AB, and T of AB is going through this point, okay, and you will get a different value for T of CD. So, average of T CD is going to be not equal to average of T AB. That is the point I am making, okay. If they are not going to be equal, that means it depends upon the surface. That is what I said earlier, okay. So, this clearly shows surface, okay. So, let me just say that what have I done? Let me summarize what I have done so far. I am trying to show that the stress acting at a point depends upon the choice of the surface, okay. I am taking 2 surfaces, this is S1 and this is S2. Over S1, I have split the integral in as OA, AB, BO, okay. OAB is OA average of vector over OA multiplied by OA, average of T over AB multiplied by AB, same thing. Why am I able to do this average? Because it's a very small thing. So, the variations are not going to be significant in a very small element, okay. So, I can take the average and move on, and I can use this relationship to find out what is the average on AB. I choose another surface, I can use the same stress equilibrium and find the average over CD, and clearly they are going to be different. Okay, they can be different. Okay, so the point is the stress acting on a surface depends on the orientation of the surface. What I want to do next is not throw up my hands in despair, but try to use this principle of stress equilibrium to get a mathematical relationship for finding T, okay, over an arbitrary surface in terms of the T over standard surfaces. That is what we are going to do now. We are going to find an exact relationship. So, that is the next step, which is, so we will find the average of T over a surface using the principle of stress equilibrium in terms of stresses over known standard surfaces. Okay, and we will do the derivation for a 3-dimensional case, but I just want to tell you that in 2D, for example, this is OAB. OA and OB are classical x-axis, y-axis. That is what I mean by standard. So, I want to find it at AB. Okay. So, basically, how is the stress along AB related to that along OA and OB. OA and OB are my x-axis, y-axis. That is what I mean by standard. Okay, OA and OB are OB is x-axis, OA is y-axis. So, they are standard surfaces. So, for a given situation, if I can define what the how the stress is here, I want to make a relationship of this stress on AB, which is some arbitrary thing I have drawn. In this case, it's a straight line, and there is a point here on which I am trying to find out. Okay. So, this exact relationship we will obtain by using the principle of stress equilibrium. Okay. We will do that next class.